All right. Hey, what's going on today, guys? So we have finished the idea of the multiplication rules for exponents. We've looked at the division rules for exponents. All right. Today we're going to look at what's called a rational exponent. So if you're talking about a rational number, if you think back to the real number system, all right, a rational number is any number that can be expressed as a fraction. So that could be a positive number, it could be a negative number, it could be zero, it could be a decimal, as long as it can be turned into a fraction. So everything that we look at today is going to be a fractional exponent. All right, in order to be able to do this, you guys are going to need a calculator. So if you don't have one, you're going to want to go ahead and pause your video and get yourself a calculator, come back and join us. All right. And then we do have a Google form that goes along with this lesson, has a grand total of 15 questions. All right. So today, these are kind of some of the ideas we're going to be looking at. All right. So what is a rational exponent? How does that equate to what we call a radical or a root? And then we're going to get into the idea of an nth root, meaning it could be a square root, power of 2, could be a cubed root, power of 3. Okay, could be higher than that. And so we'll take a look at how a rational exponent and a radical symbol, okay, you guys typically would call them probably square roots, but they could be other roots other than square roots. And then ultimately, by the time we're done, how do I solve an exponential equation? Okay, that'll be the last thing we get to down here in example 5. Okay, if you're feeling good about these two here, you can go ahead and skip over this. Okay, if you are a little bit shaky on these two ideas, then go ahead, pause your video, give them a shot, and then you can kind of check to see if your work kind of matches what I have here. So if I'm looking at this first one here, first thing I would do would be to simplify or reduce. So I could turn this into a 1, I could turn this 18 into a 2, and then with my ends, using the quotient rule there, I have more ends on the top than I do on the bottom by an amount of 4. So my answer could look something like that, or I could ditch the -1 and just leave it as a negative n to the 4th over 2. Okay, so that would be your most simplified answer there. As you're looking at the second one here, you have a power outside of the set of parentheses. That'd be the first thing I do. So apply the 3 squared would be 9, x to the 4th, y to the 3rd. On the bottom, I have a 24. That x to the -2nd, I'm going to move to the top because it's negative, and a y to the 1st in the bottom. Okay, I like to kind of think about a division or a fraction there as I'm working along. So in this case, I'm trying to reduce the 9 and the 24. Looks like I can take a 3 out of both of these, leave me with a 3 and an 8. Notice here you have x's in the top, that's product rule. So that would be x to the 6th, you're adding those together. And then the y's, it's going to be the quotient rule because you're going to subtract those, y to the 2nd. So if I'm looking at my choices down below, it looks like the one that matches that is this one right there. Okay. All right, so our two goals for today, to be able to evaluate or rewrite an expression using a rational exponent. Okay, so remember that's a fractional exponent. And then the last thing we're getting into is, can I solve an equation with a rational exponent? So we will kind of get into these ideas here today. We kind of talked about some of these, working our way through. This page right here, probably the most important thing we're going to see, because it's going to explain the difference between how a rational exponent and a root are organized. So please, please, please make sure that this example here is in your notes, okay? Because what we're going to see here is that these two numbers, the 1 and the 2 of that 144 to the 1/2, that they in fact both live somewhere inside of this radical symbol over here. All right, and so we'll start first with this denominator of 2. In fact, this denominator of 2 in the radical is actually located right there. Okay, so any radical symbol or root symbol has a value sitting outside of here that tells us essentially how many identical factors we need to find in that base number. Okay, so in this particular case, would be known as a square root. And then this 1 is actually located right there. Okay, so in fact, this is the square root of 144, okay, to the first power. Or you could think of this as 144 to the 1/2 power. Okay, so what we're going to do first is kind of look at how do these two ideas kind of relate back and forth, that idea of being able to rewrite what we are looking at. But the numerator will always become the power that is attached to the base, and the denominator will be the root that we are looking for, whether that be a square root, power of 2, cubed root, power of 3, fourth root, fifth root, so on and so forth. Okay, so looking at these two right here, okay, this should not be too difficult. Write an expression in radical form. Okay, so a radical, remember, the denominator becomes the root, the base of 81, and the power is raised to the first. Now, in this particular case, we could actually write this with both of those numbers not there, because in this case, they are understood. Anything raised to the first power, we don't have to write it. It's understood to be there. And secondly, this root symbol that is out here, if it's not written there, it's also understood to be a square root. That's why most of you guys, when you see this symbol right here, would call it a square root, when in fact, really, that's known as a radical symbol, because whatever number is written right there is what root we are looking for. When we don't write it, it's understood to be a 2, and therefore it's known most commonly as a square root. Okay, so if we just kind of look at this one in the reverse, remember, if we don't see a number there, there's actually a little 2 right there, and if we don't see a power, there's a little 1 right there. So this is really the same as 38 to the 1/2 power. Okay. Looking at these two here, okay, very similar. However, in this example, okay, what's actually being taken to the 1/2 power? Is it the 12? Is it the m? Or is it the 12m? Okay, so ask yourself, which is actually being taken to the 1/2 power? Because there's no parentheses, the only thing being taken to the 1/2 power is the m. So if I was going to write this expression in radical form, then I'm going to have a 12 radical m. Okay, because the numerator is a 1, I can put it there if I want to. Because the base or the denominator is a 2, I could put the root there if I wanted to. But because those are the two understood values, I don't need them to be there in order to have the same result. Now, how does that differ from this one down here? Notice that both the 32 and the w are underneath the radical. So in order to get them out, I'm going to have to use a set of parentheses. And the power that is going to be attached here, remember, with nothing in either of those spots, would be to the 1/2. Okay, so notice how these two are very similar to each other, yet because both are underneath the radical here, they have to be in parentheses. Because there is no parentheses here, the only one that gets underneath the radical is the m. Make sure you can recognize the difference. All right, so quickly looking at those four, which one is the correct answer? And hopefully you're saying it is A. Okay, base of 16 to the 1/2 power would be the same as the square root of 16. Okay, so what if it's not a square root? What if it's what we would call the nth root, meaning some root other than 2? So in this case here, if we look at this first one, we would say that this is a 6th root. Or if we would look at the second one over here, that is a 4th root. So to simplify this, you have two options. Option number 1, I can write this as 15,625 to the 1/6 power, right? Remember, there would really be a power of 1 there. Okay, and if I use my calculator to simplify that, 15,625 raised to the 1/6 power, okay, would be an answer of 5. Okay, meaning essentially 5 to the 6th power. If you did 5 raised to the 6th power, you would also get this same value, 15,625. Or if you know how to put a root into your calculator, okay, you would have to type in something basically like this. It would be, let's move this out of the way a second. You would have to do something like this. You would put the 6 and then find the symbol in your calculator that looks like that, and saying basically that this 6 is going to go in for that root, and then the number you would put in is 15,625, and that's still equal to 5. Or you can turn this into a fractional rational exponent of 1/6 and go that route. So over here, 256 to the 1/4 power. Okay, we're looking for one of 4 identical numbers that get me to 256. Okay, so I'm looking for one of 4 identical numbers that get me to 256, and that answer is 4. Or like we did over here on the left, we could write it in our calculator like that. That was how it would look, unless you have a TI graphing calculator, the 83 or 84, depending on what version you have. Actually, this may take place on its own. It's located underneath the math option on the left-hand side, so you can find it in there. If you have a TI-30 graphing calculator, you'll see it down the left-hand side. It is the 5th button down on the left-hand side. All right, so looking at these here, okay, which one of those numbers? Now, in this case, remember, we are looking for 4. We need the same factor taken 4 times, all right? And because the power here would be a 1, we are looking for one of 4 identical factors that would get me to 2401. I think it's pretty easy to see that we're probably not going to multiply 343 together 4 times to get to 2401. I doubt we're even going 81 times. Kind of seems unlikely that we're probably going 49 times 49 times 49 times 49 to get to 2401. So without even really doing any work, just understanding how a rational exponent works, I think I could come up with that answer. Okay. So here essentially is the reverse of that. All right, so if I see that it's 1,331 to the 1/3 power, then what root am I looking for here? And hopefully you're telling yourself you're looking for a cubed root. Now, because that number is not a 2, I will have to put that 3 as the root. So my denominator of the fraction becomes the root, and this is 1,331. If you want, you can put the first power there. If you don't want to, you don't have to, because the 1 would be understood. Okay, so, and to find that result, okay, this would be equal to 11. Essentially saying 11 times 11 times 11 would get you to 1,331. In this second one over here, it is not a cubed root. It is what's known as a 4th root, because the denominator of the rational exponent is a 4. Okay. And that would be the 4th root of 2,401. Okay. Or what number taken to the 4th power would be equal to 2401? And that number is 7. All right. So just looking at this one here, again, if you're looking at the denominator of the root, or of the rational exponent, it is a 4th root. So it could be thought of that way. In your homework, you'll be asked to make the transition between these 2 statements here, between the rational exponent and the radical, or the root. And you'll also be asked to make the transition between the root and its simplified answer, meaning which of these choices satisfies that statement. Okay, so in this case, that number is 8. All right, if you're putting that in your calculator, remember you would be doing 4. You're looking for that symbol, which basically says you put the root in, and then we would put the 4096 after it, and we would find out that answer is equal to 8. So everything we've seen to this point has had a rational exponent with a numerator of 1. So what if it's not a 1? Okay, so something like we see here, the rules don't change. If we look at this first one, it is still a fifth root of 32, but now it's 32 squared. That numerator is not a 1, it's a 2. So it is a fifth root of 32 squared. Over here, it's a 2, so it's a second root or a square root, but now of 81 to the fifth power. Okay. If we look back at this first one, 32 squared is really the same as 1,024. So essentially what we're asking ourselves here is, can we find one of five identical factors that will equal 1,024, okay, or a fifth root of 1,024, and that is 4. Okay, over here we're looking for a square root. 81 raised to the fifth power is a huge number. I guess I can write it here. Better make that a heck of a lot longer. 3, 4, 8, 6, 7, 8, 4, 4, 0, 1. Okay. Or if I'm up here, I don't need to transfer it from 81 to the fifth into this giant number. What's that? 3,486,000,000. Okay. That is a square root of 81 raised to the fifth power. And that answer is 59,049. So if you took 59,049 and squared it, you would end up with that result. All right. So last one before we look at our last example. Okay. If I'm going to rewrite this, it is a square root because the denominator is a 2 of 36 to the third power. Remember, you're going to need a calculator here for today's lesson. So a square root of 46,656. Remember, because it's a square root, I don't have to have that root written there. Okay, so a square root of 46,656, and that answer is equal to 216. Okay. So being able to manipulate a rational exponent into two things, a power and a root. Okay. Please remember how those two are related. All right, last thing we're going to get into is how do I solve a rational or an exponential equation? Okay, if you look at this here, basically what it's trying to tell us is that if we can figure out two identical bases, then we can take our exponents and we can set them equal to each other. Okay, so if 5 is equal to 5 as far as the bases, then the exponents have to match. If the bases are both 4s, then the exponents have to match. Okay, so we're going to look at 3 examples here. Okay, these are our last 3. This is how your work will end today. All right. So as you look at this, 9 to the x is equal to 729. Well, right now, these two statements don't match each other. But because this has a base of 9 on the left-hand side, the goal will be to write 729 with a base of 9 as well. So can we find 9 to a power that is equal to 729? Can I come up with a number right there that makes these two equal to each other? And if you take your calculator and try a couple things, you should quickly be able to find out that 9 to the third is equal to 729. So because the bases are the same, they're both 9s, then that must mean that x is equal to 3. And I have solved this equation. Okay. If we come over here to the second one in B, because the base is a 4, then I want the base over here to be a 4 so that I can set the exponent on the right equal to the exponent on the left, and I can solve. So take your calculator. 4 to a power that is equal to 1,024. 4 to what power is equal to 1,024? Okay, if you solve that, you're going to find out that 4 to the fifth power is equal to 1,024. So if the bases match, they're both 4s, then that must mean that the exponents match. So that must mean that 3x has to be equal to 5. Well, if 3x is equal to 5, and I divide both sides by 3, then x is equal to 5/3, or you could say 1.6 repeated. Okay, probably easier to leave it as 5/3. So if you want to solve an exponential equation, you must make the bases on both sides match each other. So as we look at this last example, it has a base of 2 raised to the 2x minus 1. I'm looking for something that is equivalent to 128, but I have to use a base of 2. Why do I have to use a base of 2? Because the base on the left side is 2, so the base on the right side has to be 2. So 2 to what power is equal to 128? Okay, figure that out. You're going to find out that it's a 7. If the bases match, then the exponents have to match. So all I have to do is solve this statement. All right, so if I add 1 to both sides, I get 2x is equal to 8, which means x is equal to 4. Okay, so your homework tonight is going to follow this idea. It's going to start out with being able to convert between radical expressions and roots, radicals. Okay, so remember, the numerator becomes the power of the base, the denominator becomes the root. It'll end with you being able to solve an exponential equation. If you guys need anything or you're confused, office hours today at 1:15. Use the last name Conklin. Have a great day, guys.